I now call to order the lecture portion of the Society's 2,533rd meeting in what is now the 155th year since its founding on March 13th, 1871. Good evening, everyone. My name is Larry Milstein. I am the president of PSW, one of the oldest scientific societies of Washington, D.C., committed to providing a forum to further scientific understanding and inquiry. Welcome to our members, guests, and friends, to the lecture part of today's PSW meeting, and to the lecture by Bill Diamond on the history, science, and relevance of the search for life beyond Earth. Before we begin, let's thank our sponsors. First, our full-year sponsor for the 25-26 lecture season, PSW member Mike Helton and Helton Associates. Thank you, Mike. And PSW member Joe Schulman and the Schulman Foundation. Thank you, Joe. And the sponsor of tonight's lecture, PSW member Charles Clark. Thank you, Charles. We are indeed very grateful for the support of our sponsors. The Society needs financial support to meet its expenses, which are not inconsiderable at this point. If you have the wherewithal and you haven't given, or feel you can give more than you already have, please do not hesitate to donate. If you are interested in sponsoring a lecture or a semester or a full year, please don't hesitate to come talk to me or to Robin Taylor or to email us. We will be very happy to discuss with you the possibility. I am pleased to announce the following new members. Aisha Tani, a Zoogler on a break, interested in space and medicine who learned a PSW from the internet. Yavuz Anatar, an architect with NOA Architects, interested in science and technology, and in particular the history of science, who learned a PSW from PSW Sarah Miller. And Susan Rich, a psychiatrist, broadly interested in science, particularly the neurosciences, as you might expect, learned a PSW through the Cosmos Club. And she says me, but I'm not sure. I think that was after the fact. And tonight's speaker, Bill Diamond, learned a PSW from our invitation to speak tonight, and whose interests will be clear in some small part from tonight's lecture. Please join me in welcoming them all to the Society. All members are entitled to a signed copy of Volume 17 of the PSW Bulletin. This is a compendium volume that has a lot of the formative documents of the Society, a list of the original members, why it was called the Philosophical Society of Washington, by which they meant science. A list of our Henry speakers, Nobel Prize winning speakers, and some other interesting things. In addition, all members are entitled to attend the pre-lecture receptions and dinners with the speakers for camaraderie, interesting and enlightening discussion, and for making new friends and contacts, and sometimes even establishing collaborations. If you're interested in membership, you can access the membership application on the PSW website by clicking the blue Join button on the upper right-hand corner of the home page. If you're here in the Powell Auditorium, there are some business cards in the back with QR codes, and you can use those QR codes to access the membership application form. Everyone who is genuinely interested in science and willing to pay the nominal membership dues annually, which haven't increased in 15 years. I want to remind you that it's really a bargain at this point. is welcome to join, and I invite you, please, to apply. Recording Secretary Scott Matthews will now present the minutes of the 2532nd lecture by Jonathan Coopersmith on Robert Goddard and the invention of the liquid-fueled rocket, which this is the 100th anniversary of the first flight thereof.
Thank you, Larry.
Wait till you get up there.
Good evening. On March 6, 2026, members of the Society and guests joined the speaker for a reception and dinner at 5:45 in the members' dining room of the Cosmos Club. Thereafter, they joined other attendees in the Powell Auditorium for the lecture proceedings. In the Powell Auditorium of the Cosmos Club in Washington, D.C., President Larry Milstein called the lecture portion of the 2532nd meeting of the Society to order at 8:02 p.m. Eastern Time. He began by welcoming attendees, thanking sponsors for their support, announcing new members, and inviting guests to join the Society. Scott Matthews then read the minutes of the previous meeting, which included the lecture by Karen Lloyd, titled Intraterrestrials, The Strangest Life on Earth. The minutes were approved as read. President Milstein then introduced the speaker for the evening, Jonathan Coopersmith of Texas A&M University. His lecture was titled Robert Goddard and the Invention of the Liquid-Fueled Rocket. The speaker began by noting that the 100th anniversary of Robert Goddard's first flight of a liquid-fueled rocket would occur in 10 days. Coopersmith described several advantages that liquid-fueled rocket engines provide as compared to solid-fueled rocket motors. These included the ability to stop and start the engine, the ability to vary the thrust in real time, and greater energy capacity. He said that liquid-fueled rocket engines also provided significant challenges, quote, as anyone who has worked with plumbing can testify, end quote. The speaker discussed Goddard's wife, Esther Christian Kirk Goddard, claiming that she played a significant role in Goddard's achievements. Coopersmith claimed that Esther Goddard was in some way responsible for 131 of Goddard's 214 patents. The speaker said that she organized and preserved Goddard's papers and that she was an important promoter of Goddard's work. Coopersmith described some of Goddard's musings as a young boy, being inspired at least part by the writings of Jules Verne. He described Goddard's education, a B.S. in physics from Worcester Polytechnic Institute in 1908, and a Ph.D. in physics from Clark University in 1911. In 1914, he was issued his first 2 U.S. patents for a multi-stage rocket and a liquid-fueled rocket, respectively. Goddard received a grant of $5,000 from the Smithsonian Institution, and in 1919, the Smithsonian published Goddard's monograph entitled A Method for Reaching Extreme Altitudes. The speaker described some of the negative media attention that resulted from that publication, including a statement in the New York Times, which was subsequently retracted decades later. Coopersmith claimed that as a result of this negative attention, Goddard became reticent with respect to sharing his ideas and accomplishments. The speaker described how Goddard's 1926 launch laid the groundwork for the 20th century rocketry and space exploration. He showed pictures and diagrams of the rocket, indicating the locations of the gas tank, the liquid oxygen tank, the fuel feed lines, and the nozzle. Coopersmith claimed that Goddard subsequently designed and built and tested 35 rockets, showing photographs of several prototypes. In 1929, Goddard launched a rocket with the first scientific payload, which included a barometer, a thermometer, and a camera. In 1930, Goddard moved to Roswell, New Mexico, at least partly because the fire marshal banned rocket launches in the state of Massachusetts. In the 1930s, in his New Mexico lab, Goddard developed and improved several crucial technologies for modern rocketry, including turbopumps, gyrostabilizers, flight controls, automatic launch systems, tracking and recording, clustered rocket engines, and parachute recovery. During this period, Goddard received financial support from Harry Guggenheim and Charles Lindbergh. The speaker ended his talk by again mentioning the Goddard Centennial celebration and giving the website of the, quote, Goddard 100th, an organization which lists the planned events and activities. The lecture was followed by a question and answer session. A member asked about Goddard's activities during the Second World War, saying that while there were considerable advances in rocket technology, it seemed that Goddard is not mentioned. Coopersmith responded that Goddard did work on jet-assisted takeoff, or JATO, during the Second World War, but he was aging and in poor health during this period. President Milstein asked about the difficulties of obtaining liquid oxygen, one of the primary fuel components for liquid-fueled rockets. Coopersmith responded, quote, "You had to make your own," end quote. He said that this required special facilities for both the generation and storage of LOX, or liquid oxygen. A member on the live stream asked if the life of Esther Goddard was chronicled in any book. Coopersmith responded that he was sure it was, but he could not think of the title. For those interested, please check the Clark University website titled Telling the Story of Robert and Esther Goddard 100 Years Later. A member asked how high Goddard's rockets went and what was the highest altitude he achieved. Coopersmith responded, "Goddard's rockets didn't reach that high. I think 40 feet might have been the highest," end quote. After the question and answer period, President Milstein thanked the speaker and presented him with a PSW rosette, a signed copy of the announcement of his talk, and a signed copy of Volume 17 of the PSW Bulletin. He then announced speakers of upcoming lectures and made a number of housekeeping announcements. He adjourned the 2,532nd meeting of the Society at 9:08 p.m. Eastern Time. Temperature in Washington, D.C., 8.3 degrees Celsius. Weather, cloudy. Dinner attendance, 46. Lecture attendance, in person, 77. On live stream, 35, for a total of 112 viewers. Views of the video in the first 2 weeks, 316. Respectfully submitted, Scott Matthews, Recording Secretary.
Are there any other comments or corrections to the minutes? Hearing none, I will accept a motion to accept the minutes, subject to that one clarification. Second? All members in favor? All opposed? Minutes are accepted and will be posted to the website in due course. And with that, we turn to tonight's lecture by Bill Diamond. Bill is the president and CEO of the SETI Institute. Previously, he was CEO and or president of several technology companies, including Wave Splitter Technologies, Dense Light Semiconductor, Zyradia or Xradia, and Comet Technologies USA, and he held executive leadership roles at Oclaro. His work is centered on lasers, photonics, optical communications and networks, X-ray imaging systems, and semiconductor processing technologies. And he's guided the commercialization of high-precision optical and imaging platforms used in scientific and industrial applications. Much of the work has been in applied physics and advanced instrumentation directly relevant to astronomical observation and space science technologies central to SETI. At the SETI Institute, Bill oversees astrophysics and astrobiology research programs focused on detecting and understanding life beyond Earth, on planetary science, and on the origins and evolution of life on Earth, and eventually, I think, more generally. Among other professional distinctions, Bill served on the advisory board of the McDonough School of Business at Georgetown University, not too far away from here, and he serves on the board of directors of the Bay. He earned an MBA in physics at the College of the Holy Cross and an MBA at Georgetown. And will, as usual, be fielded after the lecture during the extended Q&A session. And with that, Bill, the stage is yours.
Thank you very much, Larry. Appreciate it. Thank you for that generous introduction, and good night, good evening, And greetings, everybody, ladies and gentlemen. It's a great pleasure to be here and really an honor to be in this extraordinary building and to have the opportunity to speak to the extraordinary and distinguished members of PSW Science. And, I'm always very careful when I talk about distinguished individuals and distinguished members, because once I had the misfortune of introducing a speaker and referring to his extinguished career. So I'm not going to make that mistake. That's the kind of mistake you only make once. But anyway, it's delightful to be here, really an honor, and very excited to share with you the story and work that we do at the Institute. I do note the fact that this is the 2,533rd meeting of the Society. That's quite amazing. What was really even more extraordinary to me was when Larry mentioned to me that he's been to all of them. And I thought that was really impressive and also quite extraordinary. So it is really delightful to be here. I am going to make a shameless pitch for PSW Science, because the other extraordinary thing that I learned is he said, you see all the cameras here and the cables. He said, you know who does all that stuff? He said, we've got a crack AV team here consisting of me, Larry, and a couple of others. So if you really like these lectures and want to give Larry a break, then maybe we could raise some money to have somebody else do the camera setups and the cable laying in the future. But anyway, thank you so much for this wonderful opportunity to be here. What I'm going to talk about tonight is the search for life beyond Earth. So we're going to talk about the history of that search. We're going to talk about the science and the technology behind the search, also the relevance of that search and why we think that this is among humanity's most profound quests, one of the most profound questions we have as a civilization. So click. The search for life and intelligence beyond Earth. We're going to talk about where it began. So this is sort of the history, the evolution, the origin story of this question, which is older than you might think. And we'll talk about how it works. How do we do this? What are the technologies we use? What are the scientific premises behind the endeavor? How does this proceed? How have we proceeded? What progress we've made? And then ultimately, why this matters. Why is this important and relevant? Why is it something we should care about? So that's kind of the agenda for tonight's talk. And we do think that this is a journey of ultimate discovery, that this discovery, should we discover life beyond Earth, in fact, even in its most simple form, microbial life, perhaps even in our own solar system, I mean, this moment will be among the most profound in human history. Should we find evidence of an advanced, intelligent, technological civilization, even more so. So it is rather an extraordinary quest. And I will answer one of the questions before it's even asked that I get asked most often, which is, have you found anything yet? And the answer I always give to that question is, if we had, you would know. So it is the kind of thing where we also say that, we'd better be really careful before we call a press conference. Because if we call a press conference, I guarantee you, everybody's showing up. So we'd better not have something other than, the big news if we hold such a press conference. So we're going to start tonight with a question. And that question is, what is science? Now that's a hell of a question to ask PSW Science, right? I have a lot of nerve doing that, right? Because you all say, well, I know what science is. But I think it's an important question. What is science? Because I think most people, and even I would argue some scientists, have a misconception about what science is. Because too many people think that science is the answers in the back of the book, right? It's the expert knowledge that says, we know how everything works and we know what's going on and we might share it with you if you're, so inclined and if we're so inclined. But that couldn't be farther from the truth. That's not what science is. So what is science? Well, actually, by asking a question, I gave you a clue, because science is exercising our curiosity by asking questions. And there's no accident in putting an image of Da Vinci here, because Da Vinci was thought by many, is considered by many to have been the most profoundly curious person in the history of science. One might say pathologically curious. So science is about asking questions, and importantly, it's about asking the right questions. There are differences between questions and the quality of questions that we ask. So, You know you're doing good science, actually, when every time you answer a question or you advance knowledge or you make progress as a result of asking questions, all you do is raise 10 new questions, right? And in some cases, 100. And if we find life beyond Earth, it'll be 1,000. So that's the good thing. It's sort of like never-ending job security because every time we answer a question, we just raise new ones. So that's what it is. And indeed, one could argue that the history of science could be read as a constant effort of improving the questions we asked and having water in between. Okay, so Socrates taught us that inquiry begins with questions, right? And, I'm not a historian of science. I'm by no means a Greek scholar. So those of you in the audience who are, please give me a break. But anyway, we'll talk a little bit about some of the history of this philosophy. So Francis Bacon, who's a 16th century English scientist and argued by some to be sort of the father of modern science, said formulating questions that could be tested by experiment. In other words, use empirical studies and analysis rather than an abstract thinking to do science, to answer questions, to ask questions, and so on. Einstein said that correctly formulating the problem is the most important part of addressing questions. He had what he called the 55-5 rule. He said, if I had an hour to address a problem, I would spend 55 minutes formulating the problem and 5 minutes working on the answer, right? So it's all about how we formulate the problems, how we understand them, how we ask questions and address them. Karl Popper, American scientist, said questions must be structured so that they can be falsified by evidence. That's a great way to answer questions, to ask questions. If they can be falsified by evidence, you're asking the right kinds of questions. Thomas Kuhn said that questions change with paradigms, so new questions become meaningful when there's a paradigm shift. We're going to talk tonight about two very fundamental, very dramatic, I would say, world-changing paradigm shifts, and we'll get to what those are in a few moments. But this is a really important concept, the idea that a paradigm shift can fundamentally change the nature of the questions you ask and the kinds of inquiry you do. Like imagine, for example, that if you woke up tomorrow and we discovered that, you know what, by gosh, the world is flat. Right? I mean, that would be a paradigm shift of major significance. One of my favorite t-shirts, by the way, is the NASA t-shirt that has the picture of the Earthrise, from the Gemini mission. It says on the top, not flat. We checked. So as far as I know, it's not flat. So that's not one of the paradigm shifts I'm going to talk about. But this is what I mean by something so fundamentally and profoundly upending in terms of our understanding that it changes the nature of the questions we ask. And that's a really important concept. And then Richard Feynman said that, how important it is that questions are driven by curiosity, that, we're asking questions that are fundamental and basic. They're not necessarily applied. So these are, I think, one of the most important things to consider about the nature of science, that it proceeds by asking questions and, importantly, by asking the right questions. So framing the problem is things like, what is the phenomena that needs an explanation? What is it that we're trying to understand? What variables matter? What are the things that we can measure or look at, evaluate, understand that are going to make a difference in our understanding or in our efforts to answer a question? What measurements are possible? What can we actually measure? What data can we collect that might inform the way we address this question? And lastly, what hypothesis might explain that which we observe? So this is what framing the problem is all about. And this is the nature of questions. So what's interesting at the SETI Institute, unlike lots of organizations, we only have one question. Anybody know what that question is? Show of hands. Are we alone in the universe? So that's our question. So this question, however, is really interesting in that it has transitioned over human history from the domains of religion and philosophy to what is clearly now the domain of science. And I would argue it's, in more recent times, gone one step further from the domain of science to the domain of technology. In other words, we have technologies to answer this question, and that is something new and different. So what phenomena needs an explanation? In our case, it's like the cosmic scale, the nature and prevalence of life in the universe. Is there life out there? As we look into the cosmos and understand its scope, its scale, its significance, its composition, we begin to ask questions like, well, is this the only place where we have happened, where life has happened? So that is the phenomena that needs an explanation. What variables matter? Well, I would say all the variables identified in the Drake equation. And big hello and shout out to Nadia Drake and her husband Scott, who are actually watching tonight. And I think Nadia and Thomas Zerbuchen were speakers here at PSW Science not long ago. So we'll talk about the Drake equation. This won't be the first time some of you have heard about the Drake equation, but we'll talk about it in the context of the work we do at the Institute. But many of the variables in the Drake equation are the variables that matter in terms of this line of inquiry. What measurements are possible? All kinds of measurements. So these are observational measurements in the radio spectrum and the optical spectrum. They're spectroscopic, they're RF, they're chemical, they're in situ, meaning in place, they're remote sensing, they're SETI types of measurements. So there's lots of empirical, technology-driven measurements that we can apply to this question and this problem. And then ultimately we'll get to what hypothesis might explain the phenomena that we observe. So that's our question. But there are some relevant lines of inquiry in this area as well. So these are related questions to the one we're fundamentally trying to answer, which is, are we alone? That would be, how does the universe work? Okay, so from the Big Bang to the formation of galaxies, the birth of stars, the creation of planets, and the onset of life. So how does all this work? How did this come together? Second question, how did we get here? What are the conditions necessary for life, and how did life begin on Earth? And lastly, are we alone? So have the conditions that led life to life here on Earth arisen elsewhere in the universe, and might life exist on other worlds? And if so, can we find evidence of that life? Now, interestingly, while these sound like our questions, and they are our questions. I hate it when we put those two words together, our and our. Shouldn't do that. Anyway, these are not just the questions of the SETI Institute. These are the three fundamental questions that NASA is trying to answer. So these are the three questions. In fact, I think Thomas Zerbuchen, during his tenure as the head of the Science Mission Directorate at NASA headquarters, was instrumental in incorporating these three questions as driving the science mission and perspective at NASA. So we're going to talk a little bit about the history, and the history of this question is interesting in terms of how old it is and how far back it goes. This is a question that's over 2,000 years old in terms of recorded human history. And it's probably older than that in terms of ancient philosophies and civilizations and societies and indigenous populations with their oral histories and so forth. But we'll talk about these characters like Democritus and Epicurus and Lucretius and Copernicus and Bruno and Schiaparelli and so forth. And by no means are these the only characters in this play of significance, but these characters do play principal roles that we'll touch upon briefly here, because I think it's interesting to understand the history and the nature of this inquiry, because I think it connects us more directly to how profound and fundamental this question is, and how it's not a new question. So that's the basic timeline, and you can see sort of where the Dark Ages and the Middle Ages and the Renaissance and the Age of Enlightenment fit in, and the Islamic Golden Age and the perspective of Islamic cultures in this question. So we'll talk briefly about this arc of history that covers this 2,000-year period at which our people are trying to answer, or they're at least asking this question about life beyond Earth. So there were the Greek atomists or atomists, philosophers, and these go back to the before the current era, several centuries before the current era. There was Democritus and Epicurus, and they were in the 5th and 4th and 3rd centuries before the current era. And the atomists were arguing essentially that the universe is infinite, that matter consists of atoms, small moving particles, that they are moving in the void, and if atoms combine here to form earth and life, they must combine elsewhere. So Epicurus wrote, there are infinite worlds, both like and unlike this world of ours. Now that's pretty extraordinary. This is over 2,000 years ago. But speculation was already happening at that time that there are fundamental truths and fundamental realities of the physical world that should result in life and other planets and other worlds existing in the cosmos besides the places here. And this is really perhaps the very first and explicit and expressed argument for extraterrestrial life. What I also love about this is this painting of Democritus, right? I mean, look at this guy. I mean, this is like, hey, what's up? You want to talk about life in the universe? This is the kind of guy that if I were in that time of history, I would want this guy as my professor. But in any case, very, very profound perspectives at such a long time ago. Then there's Lucretius, who wrote De Rerum Natura, which is translated as On the Nature of Things. And I don't know how many of you may have read the book The Swerve by Stephen Greenblatt, but it's an extraordinary book, and it talks about the discovery of this ancient text on the nature of things by a papal scribe in the 16th century. And the works or the content of this book were extraordinary for its time. It had unbelievable concepts and notions. So the universe is composed of atoms and the void, that the cosmos is infinite. It's infinite in extent and it is unbounded. I mean, a profound perspective to have at that point in time. There are infinite worlds because matter and space are infinite and our world is not unique. Unbelievable. The atomic swerve takes place. So atoms collide to form objects because of random swerves in the physical positioning of atoms and the onset of collisions. This in turn is introducing chance into the system, and it is because of chance that we get randomness that provides the basis for the formation of life. It gives us the physical prospect and possibility of life and free will. Again, extraordinary concept. So also, Lucretius conceived or expressed in this work the nature of life in evolution. Spontaneous generation. Life emerged naturally from Earth through trial and error. This was a perspective expressed on the nature of things. Natural selection. You know, we think it's Darwin. It's actually already a concept back at this time. Only organisms adapted to their environment survive to reproduce. This was a fundamental concept also introduced On the Nature of Things. Human progress and civilization developed through necessity and accidental discovery, not through some other divine process or intervention. Life and evolution is a result of natural processes, not divine intent or guidance or intervention. So when you think about that and you think about what came later in the Middle Ages in the terms of perspectives, these are really extraordinary and profound points of view. But again, they were philosophical and they were not evidence-based. Nevertheless, really interesting. There were, of course, some opposing views, and Aristotle most notably, and Eudoxus and Ptolemy, they conceived of a stationary, Earth-centered cosmos in which Earth was at the center and it was surrounded by rotating concentric celestial spheres, and that's how the universe was constructed. And it was a fixed and confined universe. Even Tycho Brahe, who gave us, before the use of telescopes, the most precise astronomical measurements ever made in human history, but he also was caught up in this centrist point of view, and he actually created a compromise in which he still had to have the Earth at the center with the sun and the moon going around the Earth, but he did have the other planets going around the sun. So he was starting to move things in the right direction. But lest we perceive these individuals as being somehow ignorant or blind, it's interesting to note that Albert Einstein also conceived of the universe as static, as not moving, and as constant, even though his own equations suggested otherwise. And this is why Albert Einstein put in what he called the cosmological constant to correct his math, which, by the way, wasn't wrong, to have the universe sit still. And later, of course, he learned and realized, particularly with Hubble's work, to discover that the universe is expanding, and he took out the cosmological constant, and he said, this is the biggest mistake of my life, having put it in the first place, not trusting his own math. But that's how ingrained these kinds of perspectives were and can be. And this perspective of the geocentric rather than heliocentric universe persisted for 1,500 to 1,800 years in human history, in spite of some bumps along the way to try and change it. So geocentric cosmology was the dominant theory for about 1,500 years. There were some interesting theological debates from the 13th to the 16th centuries, and these explored whether multiple worlds were contradictory to Scripture, in other words, not allowed by virtue of Scripture, or conversely, if rather that actually the idea of other worlds was very consistent with, divine omnipotence. And it was actually the Bishop of Paris in 1277 who said he actually forbade the notion that other worlds couldn't exist and that the world and the universe wasn't more complex, because he said that would be very antithetical to the notion of a God and a superior being for us to have that point of view. So there were views that countered these kind of geocentric it's all about us humans perspectives. But again, this geocentric perspective persisted for a long time. Giordano Bruno in the 16th century argued that the universe is infinite. Stars are suns. Other worlds have inhabitants. So here again, much later than the Greek atomists, we do have a perspective reemerging that no, we're not alone, at least in terms of planets and life elsewhere. There must be other places where this has happened. Then we have Copernicus and the heliocentric universe. This was the first of the two paradigm shifts I'm going to talk about. So in 1543, he published his work to suggest that what we have was a heliocentric universe, that by virtue of observation, one could actually tell, if you sort of observed carefully, took measurements, collected data, and did the math, that it was the Earth and the planets going around the sun and not the other way around. And that is really critical to understand, and he also argued that it is centrally important that what we do is describe the world as it exists by the way we observe it, rather than make stuff up because it reinforces beliefs that we'd like to retain. And so he was arguing that astronomy must describe the real physical system of the world. But this was a tectonic shift, right, in understanding. I mean, it marked a complete transformation on how humans perceive themselves in the universe, and it actually led to a broader shift to a scientific revolution. One could say this was sort of the beginning of what allowed us to think scientifically and empirically and not philosophically. And it really created the foundations for modern science and allowed modern science to flourish as an independent discipline or endeavor. And again, I don't think there's any way to understate how important this shift was. Absolutely transformative moment in human history. And we'll visit the second one in a little bit. So we also had another groundbreaking perspective offered by Christian Huygens, who speculated about alien life, and that included alien plants, animals, even alien astronomers. He conceived of this idea of aliens looking into the cosmos as we are doing. And so what's also interesting here is that his perspectives were no longer theological in nature or philosophical in nature. They were based on reasoning from observation. So this was a shift, a beginning of this shift from theological and philosophically based perspectives to scientifically based perspectives based on observation. So these are important landmarks. Really interesting is this book, published in 1686 by Monsieur de Fontenelle, and it was called it was about the plurality of worlds. It was called Conversations on the Plurality of Worlds. And it's really striking for a couple of reasons, because it was a story based on a conversation between a scientist philosopher and an intelligent, well-educated marquise, a woman, notably, at this time, while strolling through a garden on her estate. And it was written in French, not the scientific Latin pervasive at the time. So it was designed for the public. It was a book for everybody, and it was a science book for the public. It was like the first Carl Sagan or Neil deGrasse Tyson. It's what we now call outreach. So this was extraordinary. In the 1600s, we had one of the first and most important examples on public engagement of the sciences and understanding the sciences. So really interesting. And it not only explored the topic of heliocentrism, but also it speculated about extraterrestrial beings, extraterrestrial life throughout the cosmos. So as it says here, it stands as one of the first major works of the Age of Enlightenment, and it's perhaps the very first example of popular science writing. It was, as I said, the cosmos of its time. There's also evidence in ancient Indian, Chinese, and Islamic cultures on pluralism. Pluralism, in other words, being there's many worlds, not one world. So we have in ancient Indian cosmology, the Rig Veda, Mahabharata, we have the Bhagavata Purana. These describe multiple lokas or realms, countless universes, cyclical creation. Think of the Big Bang Theory, where we wonder whether this happens on a repeated basis because we get expansion and then contraction and then another Big Bang, etc. So really interesting cosmologies and theories from these early civilizations. We have Jain texts in the Indian culture as well, describing the eternal universe, infinite space, countless worlds populated by living beings. So life pervades the cosmos. So these are interesting perspectives in non-Western European cultures. Classical Chinese cosmology was also very profound and very advanced in its astronomy, although it tended to focus more on cosmological subjects rather than subjects of the search, life elsewhere in the universe. But Islamic scholars expanded on the Greek atomists and their perspectives. They did this between the 8th and the 14th century, and Fakir al-Din al-Razi in the 12th century, he argued that God has the power to create thousands of worlds beyond Earth, and some could even be larger than Earth. So this is very much like the argument made by the Bishop of Paris in 1277. So really interesting that in Islamic culture as well. So you see this all around the world in different cultures, this same perspective that this can't be the only place where things have come together. So what you end up with is this amazing convergence of perspectives. So the Greek atomists used physics. The Indian cosmology used metaphysics. The Islamic scholars used theology. The Enlightenment thinkers used astronomy. Different pathways, different perspectives, different ways of looking at the world, same conclusion. It seems unlikely that Earth and its life are unique in the universe. So that's a really interesting arc of thinking over a long period of time through and across different cultures. So then we have the first real observational astronomy and what we might call the first technosignatures. So Giovanni Schiaparelli decides to point his telescope at an event called opposition, when Mars and Earth are as close together as they get in their orbit. And this happens every 780 days. And then every 15 years, that's actually the very closest, because in fact, the orbits are not perfectly circular, they're somewhat elliptical. So every 15 years, you get a really close opposition. But he made these observations and with a 22 centimeter refractor telescope, and he noted what he called canales, or channels is the proper translation from the Italian, on the surface, but he drew them and marked them. And then Percival Lowell, some years later in the mid-1890s, made Mars observations, and he revealed what he called canals, which was based actually on a misinterpretation or a mistranslation of the word canale. But he saw these structures and the appearance of engineered phenomena on the surface of Mars. So, and he drew these pictures and said, there must be advanced technological life on Mars because we're seeing evidence of it right on the surface. Well, of course, that turned out not to be the case. The NASA Mariner 4 it took until NASA launched the spacecraft to take a closer look before we could actually disprove this idea. But Mariner 4 finally, in its flyby, disproved the presence of canals or channels or engineered phenomena on the surface of Mars in 1965. But and Lowell has to also be credited for actually pioneering modern astronomy in the idea of building observatories on high mountains with great seeing, et cetera. So an amazing astronomer. But what's interesting here is an idea for a word that didn't exist at the time that is now in the lexicon, and it's something we call technosignatures. So what's interesting is he observed features on a planet that he thought only technology could achieve, and therefore there must be an advanced civilization on that planet. So this idea that through observation we could find things that appear to be engineered and not natural in their origins was a first way of saying, oh, there must be life and intelligence on that planet. So a very interesting experience or observation. So truly engineered structures observed at planetary scale would serve as technosignatures or signs of intelligence. So technology as a proxy for life and intelligence, and that's the essence of SETI research. And it's interesting because we call SETI the search for extraterrestrial intelligence. That is actually a misnomer because that's not exactly what we're doing. What we are doing is searching for extraterrestrial technology. We're looking for signs of what intelligence can produce. We can't detect intelligence itself directly, right? So we're looking for signs of extraterrestrial technology as a proxy for life and intelligence. So we've gone from this geocentric to a heliocentric and then a pluralistic, meaning multiple worlds perspective. And that starts, with the writings of de Fontenelle and the observations of Schiaparelli and Lowell. By the 1700s, what's interesting is most of the educated Europeans and Western civilizations assumed at that point, because of what was happening at the time, that Mars, the moon, and other planets likely hosted life. So that was kind of the pervasive knowledge at that time, which is really interesting. And of course, it changed later. But we've got this 2,000-year history of philosophy, of mythology, theology, and science, all shifting our perspective from a geocentric cosmology to a heliocentric one, ultimately to a pluralistic one, or plurality of worlds perspective. And now we have this vast, expanding universe filled with galaxies on scales we can barely conceive of. And it's filled with stars and planets. The building blocks of life are ubiquitous everywhere in the universe. They are the most abundant elements on the periodic table, and most probably life and intelligence is out there too. So honestly, this is one of the great intellectual arcs in human history. And I'm going to leave you with a quote. No, I'm not leaving you, but I'm going to give you a quote or offer you a quote that I want to be famous for someday. So it could be that this is the moment when it will be recorded for all of human history and it'll say, Bill Diamond said that. But my quote, which I will confess I actually conceived of before I even came to the SETI Institute, because I used to think about this stuff a lot, is that the most remarkable thing we may discover about life is that it's not remarkable at all. It probably exists everywhere. That's not to say it isn't interesting or amazing, but it isn't remarkable. So we'll talk about how we get to that conclusion. So we go from this arc of thinking, of science, of philosophy, of observation, etc. And then we come to technology. So we had here on Earth pre-industrial societies for 10,000 years that were basically dominated by muscle power, wind power for energy, water, and biomass. Most of what we might call modern human history can be described in terms of pre-industrial societies in this capacity. So you'll see that it's 10,000 years. You'll see another thing in brackets there that says 70.4 seconds. I'll explain what that is in just a moment. Industrial societies came along more recently And for about 250 years ago, starting 250 years ago, we started using fossil fuels and had steam power and mechanization and industrialization and automation to some extent. Machines and equipment and energy and powered instruments exchanging place for, farm workers and laborers, et cetera. So that is 250 years, or about 1.8 seconds. Technological societies, mastering electromagnetism, atomic structure, material science, biomechanical processes, planetary scale energy manipulation. We've been a technological civilization for about 120 years. That, in other words, when we've been involved with electromagnetism, understanding the atom and so forth, 120 years, 0.8 seconds. What are those seconds time frame? How many of you have heard of this cosmological time scale that I think Carl Sagan introduced to us? So take the 4.5 billion year history of Earth and convert it to a calendar year and say what happens in that calendar year. 1 year, or rather 1 day in that calendar, is a little over 12 million years. Okay? And the age of the dinosaurs, which ended 60 million years ago, was about 180 million years long. That's 2 weeks in the cosmological calendar out of our 52-week year. Okay, and then you take the 10,000 year history of, modern, what we'd call pre-industrial societies or a societal-based human population. That's 70 seconds ago. So a little bit before 1 second before, or 1 minute before midnight, at the end of the calendar year, we have these pre-industrial societies. Basically, less than 1 second before midnight in a calendar year, we have technology. So that helps you put in perspective how long we've been technical and industrial, very, very short period on a cosmological timescale. And that's an important consideration when you start thinking about SETI and looking for life elsewhere. And it took until a second before midnight before we could even look for other civilizations like our own in this calendar year. So just keep that in mind as we go forward. So we've been a technological civilization since the early to the mid-20th century, when we invented the radio. And I think you had a speaker a couple of sessions ago about the history of the radio and Marconi and his invention. But so these efforts included the electromagnetic spectrum was unlocked, radio and radar electronics were developed, nuclear physics, semiconductors, optics, global telecommunications and connectivity. All of these are very, very, very recent advancements from the human species. And so these also give rise to new questions about paradigm space. So, just 120 years ago, we had a paradigm shift when we became technological that, again, creates a platform for new and different and revolutionary kinds of questions. Then there was this seminal paper that was published in 1959 in Nature in September. And it was by these two Cornell astronomers, Giuseppe Cacconi and Philip Morrison, and it was called Searching for Interstellar Communications. And so remember, this is sort of post-Second World War, when radio and radar technologies played a huge role in the technology, if you will, of that period of time and that conflict. And they speculated that one could take advantage of this phenomena of radio. And we understood that at that time that radio frequencies could transmit information over vast distances, that at certain wavelengths in the radio spectrum, the interstellar medium or the cosmos is more or less transparent, so information can go for vast distances. So what they did in this paper is they established a scientific basis for SETI as an endeavor based on searching for radio waves. They're like, we've invented radio. So presumably, any other technological civilization that's come along will have done the same thing, because radio isn't, some uniquely human thing. It is a phenomena that can be tapped into as part of nature in terms of manipulating the electromagnetic spectrum. So also in this paper, they proposed keying on a particular frequency at 1.42 gigahertz, which happens to be an emission frequency for hydrogen that spectroscopists use and astronomers use to study hydrogen in the cosmos. And they said, you know, it would actually make sense if you were an alien civilization and you wanted to see if there were any other alien civilizations out there to transmit on that frequency, because other advanced civilizations would be aware of it, they'd know about it, and they'd be thinking the same thing, that, yeah, that would be, let's look there and see if anybody is saying hello. And so it was a really interesting and groundbreaking perspective offered in this paper, and it surmised that alien technologies, again, they would be aware of the H2 line and its fundamental nature, and that the fact that it would be understood by civilizations across the cosmos. So it was really a wild, speculative, and interesting idea that was put forth. And again, they viewed this as a logical hailing frequency. You want to say hello? Here's a good way to do it. So that was an extraordinary paper, and it prompted an, at the time, young astronomer from Harvard, who is now at Cornell University, to actually say, hey, okay, they just gave me a great idea. Let's go do this. So Frank Drake used what was then a new 85-foot diameter radio telescope at the National Radio Observatory at Green Bank, West Virginia. So you can go out there and see it today. Today they have the great big dish at Green Bank, which is the largest moving sort of object on the planet. But you can go visit this. And he pointed that telescope, the radio telescope, at the Tau Ceti and Epsilon Eridani star systems. These are very much sun-like stars. So the idea was, well, let's look for stars similar to our own. And these are relatively close by, about 11 light years from Earth. So this was called Project Ozma, as in Oz and the Kingdom of Oz, which would be distant and interesting and full of interesting species. So it was kind of a fun way to denote the project. But he did 6 hours observations a day for a couple of months. He centered on the 1.42 gigahertz frequency, but did it around it in 100 hertz increments. So he would sweep up and down, covering 400 kilohertz frequency ranges, and did that again for a couple of months. He didn't find anything at the time. I think that I understand that he thought he did. There were a couple of wait a minute, is that something? But these turned out to be interference, aircraft or satellites or something else, which is what we deal with all the time in our world and in our work. But the most important thing was the age of SETI had begun. So Frank had opened the door for a whole new line of thinking and a whole new way of answering this question, are we alone? So what happened in 1961 is we had a question that had already transitioned from theology and philosophy to science, but now also to technology. We can apply and use technologies to address this question. So we have this interesting question, but arguably it needed a framework to pursue it and follow it. And so it was a year later, in 1961, that the National Academies asked Frank Drake and Carl Sagan and a handful of other scientists and scholars to come together and talk about whether SETI was a legitimate endeavor to undertake. Does it make sense to do this? Does it make sense to look for life beyond Earth? And actually, it's possible. Nadia Drake and Larry, subsequently, and I are going to be trying to work to figure this out. But it is possible that Frank gave a talk about his work and his first SETI experiment here at PSW Science, and somebody in the audience was from the National Academies, and it was a result of that they said to Frank, go and study this. So we've got to double check and make sure if this story is correct or not, but it would be really fascinating and quite cool if it did. Then we'd have to get a big, huge plaque in here for sure. So we'll work on that. But so Frank Drake gathered with these scholars, and it was his job to put together the agenda for the meeting. Okay, what are the things we're going to talk about to answer the question, does it make sense to look for life beyond Earth? So he thought, well, there are some fundamental things we need to understand. One of them is, what's the birth rate of stars? How often are stars born? And then, how many stars have planets? So once you have stars, are planets around, most of them, or not? Remember, this is 1961, and we didn't know the answer to that. At that point, And up until the mid-90s, we had no empirical evidence for any planets outside of our solar system. So the idea of planets beyond our own solar system wasn't scientifically proven at that point, even though astronomers, I think, for a long time probably thought, yes, there are natural explanations for why planets should exist, and they're probably everywhere, but we do not know. So how many stars have planets? How many planets are habitable, Earth-like planets? You know, they have the right conditions for the possibility of life to form and evolve. How many habitable planets go on to develop life? If there are habitable worlds, in how many cases does life emerge? If you have life emerging, in how many cases do evolutionary processes have the chance to form intelligent, complex beings or species? If you have intelligent life, in how many cases does technology arise? The kind of technology that could manifest itself beyond the confines or the boundaries of that world in a manner that we might be able to observe and look for. And then lastly, most importantly, most intriguingly, how long might technological civilizations remain detectable? So he wrote down these questions. I'd love to know whether it was on, a napkin or a menu or a notebook paper, but anyway, these kinds of details are perhaps lost to history. But he realized that he could express these questions, he could put together in these questions and represent them as variables and assemble them into some kind of formulation, which he did. And this turned out to be a roadmap for what we now call astrobiology and SETI. It basically put together the framework that was needed to identify the kinds of questions we need to ask if we're going to answer this question, are we alone in the universe? So it says the number of technological civilizations is a product of the number of stars, the birth rate of stars in the universe, the fraction that have planets, the fraction of those that are habitable, how many of those go on to develop life, intelligence, technology, and then how long do they last? And so this was also very profound. It wasn't then, nor is it interpreted now as being a formulation to give us a precise answer. I don't think that's really its purpose. But what it does is, again, provides this contextual framework. It asks the right questions. It identifies the right variables that we should be looking at. Back to this issue of what is science, it's about asking the right questions. These are the right questions. So what's interesting now is with the onset of that first SETI experiment in 1960 by Frank Drake, for the first time in human history, we've made this transition again from theology, philosophy, and science to technology. Now we actually have the technology to answer the question. That's kind of extraordinary. It's also kind of recent. So it's not very long ago. So that brings me to the SETI Institute. I'm not going to talk a lot of detail about the Institute, give you a couple of oversight perspectives on it. But at the SETI Institute, our mission is to lead humanity's quest to understand the nature and prevalence of life and intelligence in the universe, and also importantly, and we take this just as seriously, to share that work with the world, to let everybody know what we're doing and what we're discovering and what we're learning, because this is a question that belongs to everybody. So we do this through three organizational centers. We have the Center for Research, which is where we do the science and the exploration. We have the Center for Education, where we do public engagement for what I call kids of all ages, basically all of us. And then we have outreach programs to inspire, hopefully, the next generation of people asking questions. So kind of a rich and interesting history of personalities at the Institute. It was co-founded by Jill Tarter and Tom Pearson. Anybody see the movie Contact out there? A lot of hands. If you remember the movie and the character played by Jodie Foster in that movie, Ellie Arroway, that character was based on Jill Tarter. Jill was a colleague and co-conspirator, as was Frank Drake with Carl Sagan at Cornell, and she served as the inspiration for the character in that movie. Frank Drake himself was the first president of the Institute and actually left Cornell to come out and end up at UC Santa Cruz in the astronomy department and to head up the board at the SETI Institute. Nobel laureate Baruch Blumberg was also on our board, as was Nobel laureate Charles Towns, who invented the laser and the maser. I think Baruch Blumberg has also been a speaker at PSW Science. Carl Sagan, Lou Platt, the first CEO at Hewlett-Packard when it was the real Hewlett-Packard, not a printer company. I won't go more into that. David Newman, who was the deputy director of NASA during the Obama administration and the head of the Media Lab at MIT. John Gianandrea, head of AI at Apple. Avery Wang, anybody have the Shazam app on your phone? You can thank Avery if you do. And for him, it was all about the math. He's, by his own admission, he knows nothing about music. But he thought it was a cool problem. Minnie Wadhwa, who's the head of planetary and earth science at Arizona State University, but is now at the Scripps Institute. Brother Guy Consolmagno is the Vatican astronomer. He's on our science advisory board. Some of you may not even know that the Vatican has an astronomer. They do. Brother Guy is an MIT PhD astrophysicist and also a Jesuit priest, and an absolutely amazing person, and also an author of some interesting books offering perspectives on science and theology and how they might work hand in hand. David Grinspoon, I think, has also been a speaker here at PSW. He held the first chair of astrobiology at the Library of Congress, and again, a really wonderful speaker and offers very interesting perspectives on this topic of SETI and also anthropomorphism, which is something he's very interested in. All right, so we're going to get to now the nitty-gritty. How am I doing on time? Because I got about 3 hours left to go. All right, so 3 ways to look for life in the universe. The first is in situ instruments. In situ means in place. That means sending hardware that can make measurements, do analysis, and look for signs of life to the place of interest. That's what, for example, the Perseverance rover on Mars is exactly an example of an in situ instrument going to a place of interest to look for life. There's a mission right now, as we sit here, flying out to Europa that will get there in, I guess, a little under 60 years now, 5 odd years, to fly through the plumes of Europa and hopefully collect samples that might have organic compounds or other evidence of life and biology on that icy moon, which, by the way, is outside the habitable zone of the sun. So, you know, these are in situ technologies designed to search for life in the universe. The next way is remote sensing, where we use instruments like the James Webb Space Telescope, which has the ability to do what we call spectroscopy or spectroscopic analysis of exoplanet atmospheres. So it can actually look at the thin veil of atmosphere of a planet orbiting another sun elsewhere in the galaxy, and it can understand the composition of that atmosphere and whether or not the composition of that atmosphere would hint to the presence of life on the surface. So that's remote sensing. And the third method is SETI observation. So we'll talk about each of these, a little bit about how they work and what the limitations and benefits of them are. They are all important. They are all parts of the toolbox we have at the SETI Institute for this endeavor, and we'll go into them a little bit. But so we have these 3 methodologies. We've got a contextual framework in the Drake equation. So let's talk briefly about the scale of the problem. How big is this problem? So it's a little helpful to understand the scale of the problem. So let me introduce you to our solar system. Anybody unfamiliar with the solar system out there? All right. So how do you do solar system? This is it. In our solar system, we have 8 planets. We have 5 minor planets. We have about 283 identified moons, 3 of which have been found by scientists at the SETI Institute, 2 around Pluto and 1 around Saturn. We also have 3,600 known comets. We have 1 million asteroids, or likely more. It's about 10 to the 16 meters in diameter. And if you're a photon of light traveling at the speed of light, you can traverse the 3.7 billion miles between the sun and Pluto in about 5.5 hours. That's at the speed of light. And if any of you ever are suffering a sleepless night and you're looking for some way to go to sleep, there is a YouTube video that follows a photon of light in real time from the sun to Pluto. It's 5.5 hours. There is no edge of your seat drama. There's no plot twist, and it is not action-packed. But it may put you to sleep. So think about that next time. But I mean, you know, it's extraordinary. We think of light instantaneously. We turn on a switch, the lights come on. It's not. It's actually pretty slow. And it's actually a pretty fundamental limit in terms of the physics of the task that we're endeavoring to do. If you're launching a rocket, you could launch a rocket like New Horizons, and the travel time would be 9 years. And that would be at chemical rocket speed. And that's what it took the New Horizons spacecraft to get to Pluto. New Horizons is the fastest moving physical object that humans have ever built that isn't traveling in an orbit and therefore getting gravitational assistance or isn't a subatomic particle. It's the fastest moving object we've ever built, traveling at 56,000 kilometers per hour. And now it is already beyond the Kuiper Belt, heading out towards the outer edges of the heliosphere and the edges of our solar system. If you took that spacecraft and you said, let's go to Alpha Centauri. We ran out of sugar. We're trying to bake a cake. We need to go to our closest neighbor and get some sugar. No problem. Get in that spacecraft. 80,000 years from now, you'll get to Alpha Centauri. That's our closest neighbor at 4.2 light years away. So the scale here is something really interesting to appreciate. So if we step out of our solar system and now look at our galaxy, the Milky Way galaxy, so the solar system, our solar system, is sort of on the edge of one of the spiral arms of the Milky Way galaxy. It's important for you to realize, I want to be a disclaimer, this is not a photograph of our galaxy. Okay, that has not been done before. We've never been far enough away to take a picture like this, and we probably never will. But this is a similar representative spiral, ordinary spiral galaxy, similar to our own, and we're sort of out at the edge. And, you know, the little circle represented here would be billions of times larger than the space actually occupied by our solar system. Our solar system is 100,000 light years across. So it would take 100,000 light years for a photon to travel from one end to the other instead of the 5.5 hours. Now, that's a movie you definitely don't want to see. None of us have time. But in the galaxy, in our own galaxy, there's an estimated candidate number of habitable worlds of between, say, 10 and 60 billion. In terms of scale, the diameter is about 10 to the 21 meters, so we'll come back to that. But keep that in mind, 10 to 60 billion potentially habitable candidate planets in our galaxy alone, and I'll explain how it is we have derived that number or that estimate. Let's go out even further. We'll take a look at the James Webb Deep Field image that was taken in July 2022, not long after the first light of that telescope. And that would be that image that you see if you took a square millimeter and held it out at about arm's length. That's sort of the size of the field of view of this particular image. And what you're seeing in this image is not stars, but galaxies. All those smudges, all those funny little things are galaxies. And the ones that look distorted are being distorted by what we call gravitational lensing. So that is also something we now understand as a phenomena that it was at first theoretical, but is now observational. So the scale here is just beyond comprehension. There are hundreds of billions of other galaxies, just as we estimate there are 200 to 300 billion odd stars in the Milky Way galaxy. So what's interesting about the work we do is the extension of scale that is involved. Because if we look at amino acids as the building blocks of life, you know, sort of the precursor components of proteins, which are fundamental to life, you know, these amino acids are on the scale of, 10 to the minus 9, so about a nanometer. And then we go to the scale of our galaxy, and we're at sort of 10 to the 20 meters. And then we go to the scale of the known universe, and we're at 10 to the 26 meters. So we are at like 35 orders of magnitude of scale that we are examining or inquiring about in the context of the search for life beyond Earth. So it's rather extraordinary. I had the opportunity to speak to an audience at Reid Hoffman's Masters of Scale conference, which he holds in San Francisco every year. And I spoke there last year, and I was a little wise guy. I said, you guys don't know anything about scale. But anyway, so we've now talked about a framework. We've talked about basic technology. We've talked about, the arc of the question. But we have something else missing, that if we're going to talk about life, life needs a home, needs a place to form and to develop. And so, the scale is one thing, the methodologies for looking are another, but you need planets. So now we have the dawn of the age of exoplanets. So what do you see in this picture? Anybody? Milky Way. And what's it composed of? Stars. Wrong. I mean, of course, you're right. They are stars. But they're not just stars. They're solar systems. What we now know, which still, I think, for the average person is not really well known, is that statistically speaking, every star in the sky is a solar system. And that is another paradigm shift, right? That's an extraordinary, world-changing, worldview-changing bit of knowledge that we now have that's empirical, scientific, observational-based knowledge. So we'll talk about how we've gained that knowledge and it's what I now call the new Copernican revolution, the second Copernican revolution. The first one being, the Earth goes around the sun, not the other way around. But now we have the age of exoplanets, and there are three main characters and a telescope that I think we can credit with the Copernican revolution. And that's Didier Queloz, Michel Mayor, Bill Baruch, and the Kepler Space Telescope. So the first exoplanets were observed by Michel Mayor and Didier Queloz. They didn't know that's what they were observing initially, but they were looking at this star system, 51 Peg, and they discovered a phenomena that was interesting using a method called radial velocity. And in this method, what they were observing was if we look at this star over time, the reason Hubble was able to determine that the universe is expanding is he noted the spectral lines of atomic spectra that were in the wrong place because they had been Doppler shifted by the fact that the universe is in motion. Everything is moving away from us. So everything appeared to be red shifted, just like when the fire truck goes by and the frequency goes down. Here, the same thing happens. The wavelength goes longer, the frequency goes down, and the spectral lines are all red shifted. And that was extraordinary. It's like, oh my God, this is moving and it's all moving away from us. Well, what happened is they're observing these stars and they're saying, well, wait a second. Sometimes it looks like the spectral lines are red shifted, moving away from us. Sometimes it looks like they're blue shifted, moving towards us. Well, what does that mean? Well, it means the star is wobbling. Well, what would cause a star to wobble? Well, probably the presence of some massive object right in front of it that is orbiting around it. So the center of mass is not the middle of the star any longer. It's a little bit out. So the star's wobbling. And it was Queloz and Mayor that figured this out. These observations had been made before, but what they did, which is I think what happens a lot of times in Nobel Prizes, is they had the right perspective and they understood the phenomena that was being observed, and they came to this conclusion. So this process of radial velocity gave rise to the discovery of the first exoplanet. So 51 Peg B, a gas giant. It's bigger than Jupiter. It's lower density, about, 0.8 the density of Jupiter. It has a 4.2-day orbital period. Remember, Earth goes around the sun in 365 days. Jupiter goes around the sun in, I think, 30 years or something like that. And but 51 Peg B is going around its star in 4.2 days, and it's as big as Jupiter. That's some acceleration, but and that's why it was observable in this phenomena. So it was really extraordinary. And this star system is about 50 light years away. So and for their efforts, they shared the Nobel Prize in 2019 in physics for this discovery. I think it was probably deserved. It's pretty profound. So, but that gave rise to the discovery of a planet, not a habitable world. Too close to the star, too big, gas giant, not a rocky world. So what about habitable worlds? Could we find habitable worlds which would be smaller and therefore much more difficult to find? Remember the picture we had on the scale of the solar system, the Earth was this tiny little dot, right? Third planet from the sun. So how do we find these kinds of environments? Well, Bill Baruch thought we could build a telescope. He's a scientist at the NASA Ames Research Center in Mountain View. He thought we could build a telescope that would look at so-called the transits or the transit phenomena in which a planet orbiting its star, if you're looking at the star and you're observing the brightness of that star over time, you'd see, if you're staring at it for long enough, periodic dimming of that of the light that you're measuring. Now, in the case of a Earth-like planet around a sun-like star, that would be a very, very tiny amount, like 1 part in 10,000. So nowhere near the size of the big dip you're seeing in this animation. And of course, the telescope is not also seeing a big orange blob like this. The telescope was looking at tiny individual points of light, about 200,000 of them or more in its field of view. So actually, Bill Barucki went to NASA 4 times with this idea, and 4 times they said, no, Bill, this is crazy, it's never going to work. And he didn't get funded. Then the 5th time, I think they surrendered. This guy is persistent, and what if he's right? And so they funded him, and the Kepler Space Telescope was built and launched in 2009. And here's what Kepler discovered. So this was what was known about planets around other stars before Kepler. And you'll see there's a lot of big Jupiter-sized planets, Neptune-sized planets, et cetera, big and massive and therefore easier to discover. And they were discovered mostly by the radial velocity method, some by ground-based observatories using the transit method. And then Kepler came along. That's what Kepler found. Thousands and thousands of planets, and most of them between sort of the size of Mars, which is substantially smaller than Earth, and Neptune, which is substantially larger than Earth. But that center was like Earth size. And a nice rocky environment in the habitable zone of a star would be a really interesting place to look for life. So suddenly we have this unbelievable discovery that says, planets are everywhere. And statistically, we can determine that every star in the sky has planets around it. So how do we know that? Well, what's really interesting is the probability that an orbital alignment is in your field of view, if you're looking at a star from a distance, goes as the ratio of the radius of the star plus the radius of the planet divided by the radius of the orbit of the planet around the star. And since the kind of planets we're interested in are really small, you can really approximate that to say if you take the radius of the star and you divide it by the radius of the orbit, that'll give you the probability. Well, if you take so if you got R star is the stellar radius, A is the orbital distance. So an Earth-like planet around a Sun-like star, that the probability is going to be 432,000 in the case of Earth, and the radius of the Sun is 432,000 kilometers. Or miles, and we've got the 93 million miles of the radius of the Earth's orbit around the Sun. So you do the math, and that comes out to 0.0047 or 0.5%. So in other words, you only have a probability of less than 1% of having a planet lined up in your line of sight to measure planets. So if you see thousands of them, you just kind of do the math. If you find 2,300 confirmed planets, which the first part of the Kepler mission found, and you're looking you've got and you do that math, you divide that 2,300 by 0.005, you get 460,000. And even if it's a bigger planet, and therefore the number's a little lower, maybe it's 2% instead of 0.5%, it's still 115,000 would be the number of implied planets. And when you're looking at a field of view that has a couple of 100,000 planets in it, you basically come to the conclusion that all the stars have planets around them. That is now widely accepted as scientific fact by the scientific and astronomical community, that statistically every star in the sky has one or more planets around it. And many of the planetary systems we have observed do in fact have multiple planets, not just one. So statistically, every star in the sky is a solar system. So what the Kepler mission taught us is that every star in the sky has one or more planets. The majority of planets fall between sort of Mars and Neptune, kind of Earth size in their physical size. About 20% of those worlds we know are kind of rocky, they're Earth-like in the habitable zone of their star. So you translate that out and you estimate tens of billions of potentially habitable planets just in the Milky Way galaxy alone. That's an extraordinary number. So this is what I call the second Copernican revolution. This is the second of the 2 paradigm shifts I was talking about at the beginning. Again, the first being that, hey guys, we go around the sun. So this is absolutely fundamental and phenomenal and groundbreaking. So let's go back to those methodologies. So we have in situ or in place. It means send the hardware to the place of interest and use different instruments. You can do ground penetrating radar, spectroscopy, camera systems, seismometers, X-rays, gas analysis, drills, probes, et cetera, et cetera. So all kinds of things you can do if you can physically put the hardware where you want it. But that's limited to our solar system. And as you saw, that's not very big. So then you have remote sensing. It's non-contact observation by flyby missions, orbiting spacecraft, ground or space-based telescopes. James Webb, as we note, can probe exoplanet atmospheres. But all of that methodology is limited to about 300 light years for small Earth-like planets, the ones of interest, maybe up to 1,000 light years or more. But the total population of planets it can evaluate is a few dozen. And bigger planets, maybe as many as 100 or so. So it's a fairly limited parameter space. Really interesting and very cool what it can do, but a very limited parameter space. And then you have SETI observations using radio telescopes or optical telescopes to look for engineered phenomena or signals that are coming from outside of our solar system, and they're distinct from what nature produces. So these would be radio signals. These would be like laser transmissions. There's a laser nearby our office up in Livermore, California, at the Lawrence Livermore Labs. It's being used for fusion energy experiments. It's the most powerful laser in the world. If you bounce the output of that laser off of an 8-meter class telescope mirror into space, it would be 10,000 times brighter than the sun. So it makes it an interesting kind of phenomena to look for in addition to radio waves. You can look at optical pulses. What's interesting about both of these things is they also give rise to another realization. We can't look for a technology we haven't yet invented ourselves, right? So there is some constraint about our own level of advancement in terms of what we can do and what methodologies we could deploy to look for signs of technology elsewhere. But nevertheless, it is expanding. There's more things and more ways, in different ways, we can do this search. But what's interesting about SETI is its parameter space is much larger than these other two methods of in situ or remote sensing. We can interrogate the entire Milky Way galaxy. And if a signal is strong enough, in principle, we can look at phenomena outside of the Milky Way galaxy. We can already make measurements of so-called fast radio bursts and other astronomical phenomena that are outside our own galaxy with our radio telescopes. So extraordinarily sensitive. You probably have seen in the movies or heard of the big Arecibo dish that was in the mountains of Puerto Rico. It was in the movie GoldenEye and other things. And before that spectacularly collapsed a few years ago, it had the world's most powerful transmitter on it, which was used to ping asteroids. So we could characterize asteroids and potentially identify those that might be a threat. So about 40% of the time of that telescope was funded by NASA to do that work. And if you had that transmitter on that telescope, and you had another one just like it on the opposite side of our galaxy, they could see each other. So pretty amazing. But anyway, so SETI just really expands the parameter space that we can do. And just to digress for a moment on remote sensing and biosignatures and how James Webb works. Okay, so spectroscopy, the detection of biosignatures in planetary atmospheres. You have light from a star, and you break it up with a spectrometer so you can see its spectrum, and you'll get the spectral lines that relate to the atomic composition of that star. And then you pass the light through, you can look at the light shining through the rim of the planet, and you'll get the spectroscopic lines of the atmosphere of that planet. And then you subtract the spectral lines of the star from the spectral lines of the planet, and you have just the spectroscopy of the planet, and then you start breaking that down, and it can identify the compounds in the atmosphere of that planet. So that's the method of remote sensing that James Webb uses. So you can identify molecules like water or methane or CO2 or what have you that might be biomarkers or so-called biosignatures that would indicate the presence or possible presence of life on the surface. So, that's how that technology works. And it's really interesting. So exoplanet atmospheres, they might suggest, not definitive, the presence of life or technology on the surface. And that would be based on, an unstable atmosphere. You'd say, like, this composition wouldn't be stable if there weren't some engine on the surface emitting some sort of gas that would keep the composition looking the way it does. Or it might be the mix of observable gases. This combination is too weird to not have the involvement of biology. Or it might be the presence of specific biomarkers, which we have yet to identify, but like methane has been a candidate in the past, but there are abiogenic sources of methane, so we can't say that methane always equals life, but things like that. So, or a possible technosignature in a molecule where this molecule isn't one that nature produces, like the kind of polluting molecules we have in our own atmosphere. If you spotted those, you'd say, there's technology and industry on that planet, because otherwise they wouldn't have that gas in the atmosphere. So if we compare the methodologies we have in situ or in place, as mentioned before, it's limited to our solar system. There's lots of intriguing candidates: Mars, Titan, Europa, Enceladus, even some speculate in the clouds of Venus there could be life. But we don't have any indications of intelligence or complex life. And as we noted before, it would take 80,000 years to try and do in situ work in some other solar system, right? So we can only do it here right now. Second, we have remote sensing. We can do targets of interest, but not too many of them and not too far away. And it's also like not definitive. We could say, well, what we see suggests the possibility, but it isn't definitive. SETI, however, gives us a parameter space that's much greater. So it's capable of interrogating the largest space, and it does include constraints that are sort of human-made or anthropocentric, but AI can significantly reduce those. Like, we typically are looking for a narrow band radio carrier frequency, and that is because that's a logical thing to look for. But, if the aliens are doing something else, then that perspective is inappropriate. But then we can use AI to say, well, don't look for narrowband carrier frequencies, just look for anything weird that nature doesn't produce, and that would be interesting. Tell us about it. So the SETI programs at the SETI Institute include the Allen Telescope Array in Northern California, which is a 42-dish array of 6-meter telescopes. We have the Very Large Array in New Mexico, where we partnered with the National Radio Astronomy Observatory to build a commensal observing strategy on that telescope that's perhaps the most comprehensive SETI research effort ever undertaken in human history, I would argue. And then we do optical SETI, where we're looking for these laser-type phenomena, and we have observatories in Puerto Rico, in Northern California, in the southwestern United States. We're about to put one in Saudi Arabia, and perhaps one in the Kingdom of Bhutan. So these would be sort of all-sky, wide-field observers to look for laser phenomena or technosignatures. For those of you who are sort of like data analysis freaks and like those kind of statistics, at the VLA and the ATA, we're ingesting and processing data at about 3 terabytes per second in real time. We're using NVIDIA GPUs and their Holoscan AI platform, so it's really bleeding edge technology. It's a complete game changer. And AI, for its part, in the work we do, and you're going to hear more about this in a talk coming up in May from a couple of my colleagues, but AI is like having another instrument. It's not just a data analysis tool. It's like having another set of eyes or another instrument that makes a different kind of measurement. So it's really profound in its implications, just the way the radio telescopes themselves have been profound. So stay tuned in terms of what we're might be able to discover. So at the Institute, back to the Institute briefly, we have one science question: are we alone in the universe? We have 3 domains of inquiry through which we explore that: the structure of the universe, planets and habitability, life, complexity, and intelligence. And then we pursue that through 6 disciplines. So we have 115 scientists. They're organized under the disciplines of astronomy and astrophysics, exoplanets, planetary exploration, astrobiology, climate and biogeoscience, and then radio and optical SETI. So that's the spectrum of work we do at the Institute. What we do is we work across the sciences. We support NASA science missions. We do field expeditions, laboratory research, theoretical work, optical and radio astronomy, technology and instrumentation development. We have an instrument on the Curiosity rover, which is an X-ray diffraction system that tells us what the composition of the surface of Mars is made of, and so instrumentation development as well. And all of this is to try and understand the structure of the universe, planetary environments, and the concept of habitability, the nature and origins of life, how life began and the evolution of intelligence and technology. So a typical day at the office is, supporting missions like Cassini, like TESS, like Kepler, like Perseverance and Curiosity, New Horizons, or doing radio astronomy in the VLA, or working in the field in places like the Atacama Desert, Antarctica, or the high Andes. So it's an all-encompassing endeavor. Field expedition sites and partner observatory sites are all over the world across 7 continents. And so the work takes us to interesting parts of the world, but it's all about informing the kind of questions we're trying to answer. So the other thing I think that's interesting about what we do and how we do it is what I call connecting the dots. So one could argue that science, and we have a room full of scientists, is largely deconstructionist in nature, right? We take things apart, we compartmentalize them, and we create these fields or these domains of research, and we give them labels like chemistry, physics, biology, astronomy, geology, climate science, planetary science, so on and so on. Nature didn't do that, right? We did that. These are our constructs. These are our ways of breaking things down into components that we can understand and we can take a deep dive into. What's really important once in a while, and what we endeavor to do at the Institute through what we call a multidisciplinary scientific approach, is connect the dots. Is to say, okay, all of these in the real world, they work in cooperation or integration or combination with one another into a complex process. And that is how nature works. So putting the pieces back together from the deconstructionist view, we think is a very important approach. So that's what we call connecting the dots. So what do we know now? Where does all this stand? So let's go back to the Drake equation. And what we know now, actually we knew this arguably in 1961, we knew something about the birth rate of stars, but that was all we knew at that time. So that's pretty extraordinary that Frank had this perspective and he had this contextual framework at a time when we knew very little about the variables he identified as being important. But thanks to the discovery of the ubiquity of exoplanets and then the characterization of those exoplanets, we now know the answer to F sub p. It's basically 100%. We also have a reasonably good estimate. I wouldn't say it's precise, but we have a good handle on how many potentially habitable environments there are, how many planets or worlds. So we can go check, 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 and that's extraordinary. So we are making progress, and we can measure that progress, even though this is sort of a digital phenomena. Either we find or we don't find, but we are making progress and more efforts all the time. And then we have these 4 areas which remain the domain of the unknown, which I like to call job security. So anyway, why do we do this and why is it important? I think the first reason is curiosity. Curiosity unites us as human beings, and it explores not just the what, but the how and the why. Why do we even exist? How did we get here? And are we alone? So these are big fundamental questions. Exercising that thing which I think is common across all human species, our curiosity, is one of the things that we are engaging in this endeavor. I think the sense of wonder. So SETI and astrobiology and astrophysics, they trigger this sense of wonder and awe that our quest brings us in contact with or face-to-face with the biggest, most profound questions in science. They help us encounter unfathomable scales and try to figure out unimaginable phenomena. And it dares to ask some of the most profound questions in science. So ultimately, we search for the cosmos as well. We're holding up a mirror to ourselves and understanding what it means to be human. That's really what this endeavor is all about. It's like a mirror and a telescope. And then lastly, it's human nature. So we're social beings. We don't want to be alone, right? This is why 40% of the population thinks UFOs are evidence of aliens in our airspace. They're not. But anyway, that's another talk. I'll be happy to come back and do that one. So are we alone? Most likely we're not, but the quest continues. So I'm going to leave you with this, this movie or video, this trailer. I call this the trailer for the movie we make in real life every day. So we're going to try and see if we can get this to work.
Finding life beyond Earth is no longer a dream. It's a discovery that will likely be made during our lifetime, and it will change everything. We've been here for more than 36 years, at the forefront of a quest that many consider science fiction.
Mars is the closest planet where we might find the possibilities of alien life.
We are home to over 100 explorer scientists.
It just takes your breath away.
Our purpose is singular.
It's kind of best to understand what you have in your own backyard as you're looking up into the cosmos.
To understand the origins and prevalence of life in the universe.
What we are doing is to try to understand, are we alone in the solar system?
Why do we pursue our mission? Because the discovery of life beyond Earth will lay the framework for humanity's next steps to the stars.
We are trying to understand why we even exist.
We are the SETI Institute.
So thank you very much. You'll understand why I put that last instead of first, because I'm not going to compete with Morgan Freeman. It's not going to happen.
Okay, we have a question from Dave Rabinowitz, a member in Oregon. Dave asks, after only 1 century, new radio uses spread spectrum modulation, which is, by design, indistinguishable from noise unless you know the arbitrary spreading pattern. Why expect to detect a signal?
Why what?
Expect to detect a signal.
Yeah, well, it's a fair question. And, one of the things, as I mentioned, we are constrained or limited by the capabilities of our technology. So if we have the notion of being able, of a engineered signal, for example, being a narrowband carrier, which nature wouldn't produce, and being something that, as a result of being unique to the background, we can easily find, that's an easy thing to look for. But in a way, it's a little bit like looking for your dropped car keys under the streetlight, because the visibility is better there, even though you left them at the restaurant. So we don't know for sure that we can, that this is a viable thing to look for. And we actually just published a paper on the fact that, or what we understand the reality to be, that if you have a narrowband radio frequency transmission from an exoplanet around a distant star, there is interference or spectral broadening caused by the star itself through space weather, essentially, the interaction of the radio signal with the emissions from the star. And so what we wanted to be a nice, neat spike becomes broadened, and we don't necessarily have the right algorithms to look for these broadened signals. But now that we understand this phenomena, we're saying, okay, let's modify the algorithms so we can look for spectrally broadened features as well as narrowband features. But the other thing that, and this is where I mentioned AI and machine learning, is that with AI and machine learning, we can change the whole line of inquiry. Instead of looking for a particular type of phenomena, we can say to the AI, understand what the radio spectrum should look like for the known universe, and then show me anything different, anything at all.
Another question from the web is from Jim Talons, who is a member. Jim is asking, to what extent does SETI interact or coordinate with Carnegie Science's telescopes in Chile, which also relates to Eric's question. Eric's from Sweden. He's kind of curious, what other radio telescopes are you using around the world?
Sure. So we are very close partners with an initiative called the Breakthrough Listen Initiative. So this is part of the Breakthrough Foundation, funded by a significant donor sponsor in California. And the Breakthrough Listen Initiative is one that is based on what we either call commensal observation or buying time on other instruments. And the SETI program with the Breakthrough uses the Allen Telescope Array. They're our partners on the Very Large Array. They use the Parkes Radio Telescope in Australia, the Meerkat Observatory, which is a huge array radio telescope in South Africa, the Sardinia Radio Telescope, the Green Bank Radio Telescope right here in West Virginia, and others. So it's a growing collaboration, I will say. But traditionally, radio astronomers have been saying, no, we're not doing SETI. That's not of interest to us. And so it's been hard. But since this question is becoming more interesting and the evidence is building to suggest its importance, we're getting a lot more cooperation from a lot more observatories around the world.
One more question? Yeah. We have a question from Joel. A couple lectures ago, we heard about intraterrestrials, organisms extremely long-lived in extreme environments. Do you think this extends to the possibility for life within and outside the H zone, which I'm assuming is the habitable zone? Habitable zone? Yeah.
Yes, absolutely. And, well, we mentioned the possibility of life on Europa or Enceladus. So these are moons around Jupiter and Saturn, respectively, that we know are icy worlds. We know that underneath the ice is a liquid ocean. We know that the core of these bodies is molten. And it's not because of the size of the planet and that they have a molten core like Earth, but because they are gravitationally torqued and twisted through the gravitational field of their massive planet that they go around and the other moons. And so we know evidence of this because we see plumes ejecting through the ice, which suggests thermal energy. We know we have water, so we have heat source. We have, presumably the same basic raw materials on those moons as here in terms of the elements on the periodic table. And we have deep ocean trenches far away from photosynthesis on Earth where life has emerged, complex animal and plant life. And that's because we have thermal energy and water and nutrients, et cetera. So there's speculation to say, well, those same conditions could exist on these worlds, and we should look for them. So and one of the things we study in astrobiology at the Institute is what we call extremophiles. These are organisms that survive in extreme environments, unbelievably cold, unbelievably hot, in the middle of rocks. We find living organisms in the middle of rocks. Fungal organisms are extraordinary, and they're everywhere. And they have very often symbiotic relations with microbial biology here. So yes, these kinds of life forms are very interesting to us. We could find life forms like that in our own solar system. That would be transformational. It wouldn't be, aliens and intelligence that we could communicate with, but it would really be yet another important bit of information. It would say, okay, if it's happening like this elsewhere, just in our own solar system, outside the habitable zone, it's got to be happening everywhere.
Let's go to the red microphone.
Hello, I'm Sylvia Valentine. I'm a member. I wondered if the SETI Institute had anything to the discovery of life on K2-18b, Water Planet.
So K2-18b, I think that's the one with the sulfur compounds. Yeah, we didn't have anything to do with that specific paper. That paper was written by a gentleman at Cambridge University. And it's a little bit like the paper that was published around the phosphine discovery in Venus, in that it's kind of an edge of instrument sensitivity observation. The idea is the sulfur compound supposedly found in the spectra from James Webb of this particular planet, a Kepler planet, that's the K2 reference, this particular molecule, as far as we know on Earth, only has biogenic sources, doesn't have abiogenic sources. And therefore, if it's present, this would suggest biology on that surface. And so it's interesting. I think there's been some concern about that paper, a little bit like what I now call the Avi-Loeb syndrome of taking sparse data and drawing conclusions that are maybe not quite justified. So it's interesting enough to go back and take a closer look. But, as I said, these measurements and observations were on the very edge of instrumentation sensitivity, and you could argue that they could be noise or error or what have you. So stay tuned. It's interesting, but it's exactly the kind of thing that scientists should be doing with the James Webb data is, let's look for these biomarkers. Let's look for the weird stuff that we think only, biology would produce.
If you're in the back of the room, could you move over to your left so you won't be in the view of the camera when we have questions from the web? Thank you. And we'll go to the blue microphone.
Thank you. Michael Haken. I'm a member. So given that I think that the probability of detecting just a transient radio signal would be so negligible that the expectation of SETI is that someone knows that we're here or is intentionally more or less continuously or at least at regular or long-term interval beaming signals to us or maybe sweeping a large area. So I guess my question is, if we are expecting that, why aren't we doing that and sending out the signals? And I understand that SETI used to have a messaging arm, but it was discontinued. You please correct me if I'm wrong. But so why aren't we also messaging, sending out messages?
Right. It's a great question, and you're absolutely right that there is a fundamental assumption here or framework that is based on the fact that, for example, our planet emits what we call leakage radiation from television, radio, airport radar, et cetera, right? And that's omnidirectional. It's moving in omnidirectional. It's not high energy. It's not focused. And that leakage is very difficult to detect once you're past 10 or 100 light years, depending on the capabilities of the instruments. So if other planets are, in our nearby sort of observational parameter space are only doing like leakage, they're behaving as we are, then they'd be hard to detect. Our instruments could probably detect Earth-like leakage, depending on its nature, maybe 10, maybe 100 light years, but not much further. So there's been an assumption that yes, they would be, and that was sort of what was in the Cocconi-Morrison paper. Aliens might, want to be using a hailing frequency and reaching out to say hello. So that is part of the assumption, because then it would be higher energy, focused, and in our direction. Now, it could also be that we're in the path of an intended recipient somewhere else, but nevertheless, there is this assumption that it's a high energy directed thing. So why don't we message? This is a very hotly debated subject in the astronomical community because there are many astronomers and scientists, most notably Stephen Hawking when he was alive, who thought it's a really bad idea. Now, what's interesting to me is the first conclusion I draw from that is, if you think it's a really bad idea, you're convinced they're out there. Because if you weren't, you wouldn't care, right? So you're automatically kind of admitting that you think it's very likely that they're out there. So let's not be, stupid and go wake up somebody who might, come and eat us or do something else a little nasty. So, so there are serious scientists with serious concerns that no, that's a bad idea. It's very dangerous. Don't do it. And so we don't do it. That's the only reason why. And so at this point, from the Institute's perspective, our view on the subject is, let's be the place where the conversation happens and the debate and the discourse happens, but let's not,
let somebody else have a question.
Yeah. But anyway, that's
We're going to
why we don't
go back to the red microphone here.
Victor Galitsky, member, professor at the University of Maryland. So I was wondering if you could comment on the Fermi paradox, which says that if intelligent life is common and vast, the whole universe, we should see it, but we don't. And so I'm also wondering whether it's possible that sustainable, truly intelligent life is simply not interested in technological gadgets and expansion, and
Right.
would be the alternative.
Yeah, I mean, that's a great question. And I intentionally did not talk about the Fermi paradox because I thought it would give me an opportunity to be invited back to talk only about the Fermi paradox. So, and I'm happy to do that. But
You just gave us the answer.
well, in a way,
No, they're out there, and they decided that they do not want us to know they're there.
it could be. There are so many elements of the Fermi paradox, which first of all isn't a paradox. It's just an interesting question and observation. But there are lots of elements to that. One is it is an anthropocentric sort of perspective to assume, as Fermi was asking, that just because you now have the capability to go spread yourself across the cosmos, that you would do so. What would be the motivations to do so? I've also talked about the scale, that in spite of having millions of years, it might never be possible to do interstellar travel. Because of the fundamental limits of physics. So even if you had the motivation and the multi-generational spacecraft, et cetera, it may not be possible physically to do that. The other question is, I think, resides in the L variable, the Drake equation. How long does a technological civilization remain detectable? And one of the answers to that might be that they no longer exist, and the window of time, the length of time that they were transmitting is too short. You know, if there was a advanced civilization 1,000 light years from here that 2,000 years ago or 4,000 years ago emitted a signal, but they only lasted 500 years in terms of doing that kind of activity, and that 500-year wave of technology passed us by 2,000 years ago, we missed it. So, you know, SETI is a problem in time and space. You know, when did they occur? How long did they last? How long were they emitting signals? So a civilization may survive its technological adolescence, which is arguably where we are, but if they if they survive, they may, as you suggested, also evolve into a species which no longer uses technology that we can observe from a great distance. That is certainly possible. So that's why the L variable was noted as the length of time for a civilization to remain detectable, not just to exist, but remain detectable. So we don't know the answer to that. Frank Drake's license plate on his car very famously was N, followed by the letters EQLS, which means equals L. So however long L is going to tell us. And statistically speaking, we can also say that the only probability we have of finding evidence of an advanced civilization is if they've been around a lot longer than we have. So we're 120 years of a technological civilization in a 15 billion-year-old universe, and the probability of finding another 100-year-old civilization of technology is 0. So L has to be pretty long in order for us to be successful. And interesting question, and I can give a separate talk on this topic. It's kind of dark, but if the onset of technology in an advanced species is the effective initiation of the self-destruct button, then maybe civilizations don't make it more than a few centuries beyond the onset of technology. Climate change, nuclear holocaust, global pandemic, any combination of those things. So, and is that universal? Is that, you know, is first of all, is the onset of technology universal? At some point, does a civilization or a species get technical? And if so, how long does that last? And does it start the beginning of the end? The reason I think, back to the other question, why I'm okay sending signals, personally, I believe any civilization that has survived its technological adolescence cannot be malevolent. Because for us to survive, which is a question mark, we don't know if we have a long-term sustainability. It's not looking good, frankly. But you'd have to cooperate on a global scale. Has that ever happened on this planet? No. You'd have to have all races, all countries, all nationalities, you know, cooperating and working together in a coordinated fashion. Good luck on this planet. So, but if you do that, if you're successful, I don't know that you could be successful doing that as an evil, you know, dark civilization. So, you know, that's my perspective.
We're running out of time, so we'll take one, maybe two more questions. I think I'm going to the blue microphone somewhere.
Ciprian Ivanov, member. Given the way that AI is trained off of routine situations, is it reliable that AI would be useful in detecting useful anomalies?
Well, I mean, it depends on how you define it. What's a useful anomaly? I mean, an anomaly is either an anomaly or it isn't, I guess, in a way. Some anomalies might be more useful than others because you say, well, this is anomalous. It doesn't seem to be what nature would produce, but it's like so weird that it may not be useful. I don't know. But I think one of the great attributes of AI is as an anomaly detector. I think AI is a very, very effective tool for extracting anomalies or anomalous behaviors or characteristics from complex data sets. So I think it's a helpful tool. Is it a panacea? Absolutely not, and it should never be viewed that way.
The red microphone, Timmy, you get the last question.
Okay, I hope it's a
Better be a good
reasonable one. I'm Timothy Thomas. I am a member. I want you to posit that the answer to your question of life is no, and that we are, in fact, alone in this and all our microbes. And I'm wondering what the implications and explanation of that might be, and whether you think it has any implication to the idea that this may be a simulation that we live in.
That's a good question. Well, the first implication is I'm out of a job. So I'm very much against that theory. But I mean, it's a fair question. Again, I think that, life started here on the most abundant and very basic building blocks in the periodic table. Life used carbon, hydrogen, oxygen, nitrogen, etc. These are all the lowest numbers and the most abundant elements on the periodic table, and they're ubiquitous in the universe. Water is everywhere. It's an interstellar medium. It's everywhere. So the building blocks are everywhere, and life got started here on these very basic building blocks, and including carbon, which is like a wonderful Lego Lego block or Lego brick. And so things attach to it and you can build long chain molecules, and that seems to be very important. So, and carbon is everywhere. So I think that, that the phenomena of life is because, what we've now learned, we didn't know this until we discovered planets, but now we know the mechanism by which planets are formed. They're formed as a natural byproduct of the birth of stars. So they are a natural extension or an emergent process from star formation. I personally think that life is going to be found to be an emergent process from planet formation. Now, so that means it's going to be all over the place. That doesn't mean it's going to be like us or intelligent or technological. But I think the null argument, the null argument would be stunning, just as the discovery would be stunning. But its implications would be that, boy, nature is really weird. Because all the building blocks, all the basic materials, all the raw ingredients are like everywhere, and it only happened here. That would be even more extraordinary than the discovery. So incredible implications for sure. Yeah.
It was kind of an ascientific hypothesis because you can't prove a negative, right?
Yeah, that's right. It wouldn't survive what Thomas Kuhn said. Anyway.
So anyway, well, thank you so much, Bill.
Thank you, Larry.
A few presents. Before you depart, we have a framed copy of the announcement of your talk signed by all the members of the General Committee, not for themselves, but on behalf of all the members. We have a signed copy of Volume 17, First Edition of the PSW Science Bulletin, originally founded as the Bulletin of the Philosophical Society of Washington. It's a compendium volume, and it has a lot of interesting stuff on the formation of the organization, the founders, and why they called it what they called it, and especially the president's address to the first president's dinner, which explains how we should conduct a science meeting and the kind of discourse we should have, which I recommend to everybody to read. And by the way, I want to point out a few things, not in these volumes, but we'll do that after I thank you.
All right. Well, thank you very much.
Thank you.
That's wonderful.
Before we go, we have some closing announcements, one of which is a retrospective one to point out that this is a long-standing topic of interest to PSW. Okay. As I believe Bill mentioned, not long after the original article on interstellar communication and the prospect of actually detecting life outside of the Earth by Morrison and company, Morrison spoke at PSW, and in those days, they didn't have PowerPoints. They didn't even have view graphs. So the practice was to actually write something and then read it. And you actually read papers at meetings. And that paper that he read at that meeting is available on the web, on the PSW website, in volume 16. Now, it turns out that Frank Drake, the same year, 1961, gave the Christmas lectures, which was an annual event. And we're looking for a record of what he said there. And as Bill mentioned, we're trying to figure out whether that was the stimulus for the national academies to take the subject seriously and convene an expert group to look into it and to try and move things forward. Now, more recently, we've had quite a number of lectures on the subjects. We mentioned Thomas Zaburchin and Nadia Drake, who gave a talk at the President's Lecture in 2023 called Whispers from Other Worlds, NASA's Search for Life in the Cosmos. Steve Squires gave a talk at the 2399th meeting in 2018 on comets and the origin of life. James Garvin gave a talk searching for signs of habitability and life on other ocean worlds at the 2380th meeting in 2017. Exoplanets and the Search for Life and Exploration in 4 lectures was the Joseph Henry Lecture at the 2366th meeting in 2016. Prospects for Life and Human Habitability Around Nearby Stars, a lecture given by Carrie Liss at the 2336th meeting in 2014. And, I think I'm reading this backwards, but you can look it up. Are we alone in the universe? For the first time, we may have it within our grasp to answer this ancient question. A talk by Matt Mountain, who is the CEO or president of AURA, the Association of Universities for Research in Astronomy. And that was, I think, at the 2336th meeting in 2014. So if you're interested in the subject, there are a variety of lectures that you can access on the PSW website. All of the ones that I mentioned here, I believe, are recorded. So you can watch things in full at 1.5x if you want. And you can skip over the beginning where I do introductions. And you don't have to go all the way to the end. You guys don't know it, but we get these comments periodically when people complaining about what is that idiot at the podium and why is he wasting our time? And when we get to the lecture, and right underneath, of course, the lecture starts at on every single recording. So it's kind of funny, Anyway, our upcoming talks are the 2531st meeting will be on April 10th, which is 3 weeks from now, not 2 weeks. And the speaker will be Amy Mainzer. She is the professor of Earth, Planetary, and Space Sciences at the University of California, Los Angeles, fondly known as UCLA. She's also the principal investigator for NASA's NEO Surveyor mission. NEO stands for Near Earth Object. And she'll be speaking about planetary defense and the NEO mission to detect and catalog Earth's nearest neighbor asteroids and comets, particularly those that might at some point pose a risk of collision. And we can send our favorite movie stars then to go save us from the collision. The rest of the schedule for the rest of the spring lecture series is posted here with one exception, the Henry, which is in the works, and hopefully we'll announce it next time. But the speaker on April 21st will be Harris Lewin. He'll talk about the Earth biogenome. And then on May 29th, as Bill mentioned, we're having another speaker from the SETI Institute and a speaker from NVIDIA to discuss their use of AI in this endeavor, and in particular, the creation of an agentic AI to run the Allen Telescope Array, including defining where to look, and then acquiring the data and analyzing it and reporting it out. So we'll see what that should be an interesting talk. June 11th, we're meeting on a Thursday. Keep that in mind. And the speaker will be Earl Miller from MIT, and he'll be speaking about the neuroscience of executive function and consciousness. And then we'll wrap up the spring semester on June 26th with a talk by Doug Wallace of the University of Pennsylvania. He'll be talking about mitochondria and about diseases that are caused by dysfunctions in mitochondrial function. And then there's a members-only meeting on July 17th, which is our annual business meeting. Be sure to check the PSW website often for up-to-date information on upcoming lectures and events. Note, if you are a member, about 10 days in advance of each event, we send out an invitation to attend the reception and dinner before the lecture. And in that invitation, you will find a link to make a reservation, which requires paying some money for the dinner and giving us some information. That information is really important to us because seating is assigned and it's not random. You know, we don't take a deck of cards and throw them on stairs and then say, oh, you know, this one's an ace and that one's a diamond. No, we actually try to match people. It's a combination of who they know, who do they say they really want to sit with, what are their overlapping interests, try to make a little heterogeneity, try to give people a chance to meet new people, make new connections, and possibly stimulate collaborations. So that information that you put in about yourselves is actually read and carefully considered. So don't be shy. It's very helpful. If you are not a member, then you will not get an invitation to the reception dinner, but you will, if you signed up on our friends list, get a notice of the lecture. And you're free to share that notice with whomever you want, and you're free to invite whoever you want to the lecture. The lecture is open to everybody, and it's free. And you do not require reservations. There is a link on our website if you want to receive those notices, if you want to sync our calendar with your calendar as to the lectures. And with that, I will be quiet. Let's thank our crew. Please return your name badges to the plastic bin before you leave. And I will accept a motion to adjourn the 2,533rd meeting to the social hour. Second, all in favor? All opposed? The meeting is adjourned. Enjoy refreshments and conversation in the social hour.